Hello again, everyone. We have discussed the origin of the nuclear magnetic moment and the net magnetisation formed by spins in a magnetic field. We now turn to how this magnetisation is responsible for generating a signal in the MR scanner. First, however, I would like to introduce the concept of frames of reference. So far, we have considered the magnetic moments as precessing about the applied magnetic field B0 at the Larmor frequency. This is relative to the laboratory frame of reference, where the z-axis is aligned with the direction of the B0 field. Depending on the strength of B0, this frequency is usually in the radio frequency or megahertz range, that is, extremely fast from the perspective of an observer in the laboratory. To simplify this situation so that we can easily observe the behaviour of individual magnetic moments and the net magnetisation vector, we can transform our observation perspective to the rotating frame of reference, in which we allow the coordinate system itself to rotate about the z-axis at the Larmor frequency, that is, at the same frequency as the spins are precessing. Now, relative to the new coordinate axes x' and y', the spins appear stationary and are not precessing. This rotating frame of reference is often used to simplify the motional dynamics of the spin vectors during a scan sequence. Since the Larmor frequency is in the radio frequency range, it also requires energy at this frequency to cause excitation of spins in the low energy level to the high energy level. This is achieved with a short burst of RF energy known as an RF pulse. So if we apply an RF pulse at the Larmor frequency to excite the spins, what effect does this have upon the magnetic moments? The RF field consists of a magnetic field component and an electric field component. If the magnetic field component of the pulse, which is often called the B1 field, is aligned perpendicular to the main magnetic field B0, then the magnetic moments will experience a torque, which will cause them to rotate about the direction of the RF field B1. Here we see the magnetic moments precessing about the B0, and an RF pulse is applied along the direction of the x-axis. The cone of magnetic moments rotates down towards the xy plane, which is also called the transverse plane. And once the RF field is turned off, the moments continue to precess about the z-axis, just as they were before the pulse. But now they precess within the transverse plane. Let's take a closer look at the motion of the cone during the pulse. Notice that the cone of magnetic moments begins to precess about the z-axis as soon as it is tilted away by the RF pulse. If we view from the laboratory frame, the cone takes a spiral trajectory down towards the transverse plane. If we view this action from the rotating frame of reference, the precession is removed, so the cone simply rotates in the zy' plane down towards the y' axis. After the pulse is completed, the cone of vectors remains stationary along the y' axis. The magnetic moments are rotated by the RF pulse as long as the pulse is on. So the angle through which they have rotated at the end of the pulse is called the pulse angle or tip angle. This angle is dependent upon the length of the pulse and the power of the RF field. The higher the power, the faster the rotation, and the larger the pulse angle. The pulse is generated by an RF transmitter system and is delivered to the sample via RF coil, which is tuned to the Larmor frequency of the proton spins at the magnetic field strength of the scanner. So, for example, the pulse might rotate the spins through 90 degrees. Here we consider the net magnetisation vector rotating from the z-axis to the y' axis, a 90-degree pulse. If a pulse of the same power is applied for twice as long, a 180-degree pulse is issued and the magnetisation is inverted to the minus z-axis. As we have seen, once rotated into the transverse plane by the RF pulse, the magnetic moments continue to precess in the transverse plane. This rotating magnetisation is moving within the RF coil, just as any magnet rotating within a loop of wire induces a current in that wire as governed by Faraday's law of induction, the same applies to the nuclear net magnetisation. The precessing magnetic moments induce a current in the coil. This current is the MR signal. As the magnetisation rotates, the current oscillates at the same frequency, the Lamour frequency. This current is amplified by a receiver system in the scanner, digitised and stored on the scanner's computer for further processing. So some important points to remember. The MR signal is observed only when there is net magnetisation precessing in the transverse plane. The frequency of oscillation of the signal is the Lamour frequency and is dependent upon the field strength B0. And all spins will give rise to the same frequency only if the B0 field is uniform across the entire sample. But of course, the B0 field is not completely uniform in reality, but will vary slightly from one part of the sample to another due to imperfections in the magnet. Therefore, spins located in different regions of the magnet will potentially precess at different frequencies. For example, here we consider 3 spins, each precessing but at different frequencies. The red spin vector is moving faster than the white one, the blue vector is precessing slower, and so the 3 vectors fan out with time. This process is known as dephasing. If we have a large number of vectors, which are initially aligned along the y-axis, we can see the effect that the dephasing has upon the net magnetisation vector. Here, the yellow vector represents the net magnetisation vector, which is the sum of all of the other spin vectors. As the dephasing continues, the net magnetisation vector reduces until when all the spins have completely randomised within the transverse plane, the net magnetisation is 0. What does this mean for the MR signal that we detect in the coil? We previously saw that the signal was an oscillating sine function. As the net magnetisation is lost in the transverse plane due to the dephasing, we see that the signal decays and will reduce to 0 with time. The MR signal is known as a free induction decay, or FID. If we observe the FID in the rotating frame, then the precession is removed and the net magnetisation vector remains static, pointing along the y-primed axis. Now the FID becomes a simple exponential decay curve. What does the rotating frame mean experimentally? Well, obviously we cannot rotate the RF coil about the z-axis at the Lamour frequency in time with the precessing spins. However, we can use electronic trickery to remove the high frequency component. If the signal received is mixed together with the original RF used to generate the pulse, then that frequency component is subtracted from the signal, leaving only the frequency response of the spins. This process is called demodulation. If there are multiple frequencies present, or the RF pulse is not coincident with the Lamour frequency, then the resulting FID will oscillate at the frequency equal to the difference between the Lamour frequency and the RF frequency. Demodulation is important because it facilitates the digitisation of the signal, which at hundreds of megahertz would otherwise require extremely fast digitisers. In the next section, we will further explore the behaviour of transverse magnetisation, the reasons for its decay, and how it is possible to recover some of the lost magnetisation.